Now, Chapter 8 is about confidence intervals. So, we saw in the last chapter that the central limit theorem connects sample averages to population averages. And so, what we're going to do is we're going to use that central limit theorem to do inferential statistics. So, we're going to take results from a sample and we're going to project those onto a population. Now, whenever we do that, whenever we take some results from a sample and we project it onto a population, we have to build in some error in there because basically we can't guarantee that our sample is a true, perfect representation of our population. So we build in a little bit of room for error, and that's where confidence intervals come into play. Okay. Now, our results will be talking about averages and proportions. So in other words, we're going to do confidence intervals for averages and we're going to do confidence intervals for proportions. And that's what we'll use. Now, whenever we create a confidence interval, we're going to start with what's called a point estimate. It's basically just a numerical value for the sample that estimates the numerical value for the population. So all that means is that is the single numerical value that I'm going to assume the population has. So for instance, if I took a sample of people in this class and I said they had an average weight of 178 pounds, we could estimate that throughout Mid-Michigan College, the population has, so the population, in other words, is all students from Mid-Michigan College, has a average weight of 178 pounds. So basically, it's the single numerical value that we tell people. And this is, by the way, most of what you see in headlines. When you look at polls, polls will say something like, 60% of Americans like such and such a policy. Well, that 60% must have been a point estimate. Now, the downfall of the point estimate is that we don't know how close we are to the actual average of the population. So if I said a sample had an average weight of 178 pounds, and we just said, well, we would expect the population to have an average of about 178 pounds. Well, what if the population actually had an average weight of 185? Would that have meant our sample was really bad? Or would that have been within reason? Okay. In other words, when I have a point estimate, should the population be within like 1 or 2 pounds of the point estimate, or should the population be within 10 to 20 pounds of the point estimate? So what we do to get over this issue is we create something called confidence intervals. So a confidence interval is basically just an interval, a range of numbers where we expect the population's average to be. So for instance, in the example I was talking about, we said that the average should have been about 178 pounds. Maybe we take that point estimate of 178 pounds and we add and subtract 5 pounds from each side. So maybe we say our population should have an average somewhere between 173 and 183 pounds. So here's the deal. There's a lot of different confidence intervals. And confidence intervals are going to depend on a number of things. We'll look at those things in just a minute, but one of the things the confidence interval is going to depend on is how confident I am of my result. How confident am I that that range of numbers actually contains the population average? Now, typically confidence levels are numbers, or excuse me, are levels around like 90% or 95% or 99% or somewhere in the 90s. Okay? You wouldn't want to say, "Hey, we're about 50% confident that the result is within that range." Because 50% confident doesn't isn't very confident. So we want a confidence level that again tells us how confident we are that my average is actually in the confidence interval that I create. So you can see the formal definitions of confidence interval and confidence level here. Okay, this is how they're formally defined in the book. I define them a little bit differently on my notes because I think it makes a little bit more sense using those other definitions. So here's what we do. So like I said, in order to create the interval, we're going to start with that point estimate. We're going to start with, for instance, 178 pounds. And then on each side of that, we build in a little bit of room for error. Now, the error is going to depend on three things. One of the things we talked about in 2 slides ago, which is the confidence level. But also the error is going to depend upon the standard deviation and how big my sample size is. Hopefully that makes sense, that if the original data has a bigger standard deviation, in other words, if the original data is more spread out, then the confidence level, the confidence interval is going to be more spread out. If we want a higher confidence level, then we want to encompass more data. So we want things to be more spread out there. And the sample size is going to work a little bit different. It's going to work the opposite. The bigger my sample is, as long as it's randomly picked, the bigger my sample is, the better representation of the population it should be. Again, as long as it's randomly picked. Now here's the outline. Here's what 3 intervals we're going to use in this chapter. We're going to use what's called a z-interval, a t-interval, and a proportion interval. Let me take a brief moment to just talk about the differences between these 3. Now, by differences, what I'm talking about is where they're used. Okay, we will look at the actual formulas for each of these when we go on, but I want to just talk about where they're used here. So we're going to have 2 intervals, 2 different intervals when we're dealing with averages. One is called the z-interval and the other is called the t-interval. Now the z-interval you should use only when you know the population standard deviation. So we only use the z-interval when we know the population standard deviation. We use the t-interval when we're talking about averages, and we don't know the population standard deviation. Now, what we're going to do in practicality is we're going to know when we use the t-interval, we're going to know the sample standard deviation. So be careful there. If you know population standard deviation, you use z. If you know a sample standard deviation, you're going to use t. Okay, so for averages, z when you know the population standard deviation, t when you know the sample standard deviation. And then we're going to have proportion intervals, and we're just going to use that anytime we have proportions. Now there's a couple of little things I will say. Typically, we want to be able to use the central limit theorem. So typically, we want our samples to be fairly big, at least 30 when we use these. But you can get away with not having that sometimes as well, as we saw using when we were in the last chapter. Okay. Now, the good thing about this chapter is there's only two big types of questions. The first big type of question is, can we find confidence intervals? And along with that, can we find the point estimate and things like that? And can we interpret what those confidence intervals actually are telling us? So that's one big type of question. The other big type of question in this chapter is, can we find sample sizes? And what we mean by that is, well, how many people should we sample if I want to know a certain range of heights? So in other words, if I want my average to be within if I want my confidence interval to be a certain length, to have a certain range, the only thing I can adjust is my sample size. I said earlier that as your sample gets bigger, you're going to be a better representation of your population. So that's what we'll do. So let me start out with the formula here of the z-interval. And the z-interval, again, is when we know our population standard deviation. The formula looks like this. Now, let me explain what this is doing. So this sample average here, that's my point estimate. So what it's saying is that your population average is going to be your point estimate minus some value. And so it's going to be between the point estimate minus some value and the point estimate plus some value. Now we know what these symbols mean. Obviously, since we know our population standard deviation, we'll put it there. The square root of n, obviously that's my sample size. And one thing you'll notice here is that sigma over square root of n, that's the standard deviation on the central limit theorem. And then we have the z of alpha over 2. And I'll explain that in just a moment. But it suffices to say now that it comes from a z value that is in some way related to your confidence level. Okay, so this is the formula. Now, a couple of things about these formulas that you're going to have, not just in the z-interval, but also in the t-interval and also in the one prop z-interval, is that you should know the formulas in sort of like a matching way. So similarly to what I said in the first test, you should be able to match the z-interval formula with this, and the t-interval formula with those things. So it'll be sort of a matching situation. All right. Now, like I said, this whole thing, we see that sigma over square root of n, so population standard deviation divided by the square root of n. That tells us that somehow this is related to the central limit theorem, and that z of alpha over 2, again, I said, is a z value corresponding to the confidence level in some way. All right, so let me try to explain this connection to the central limit theorem and the z value the best that I can. So here's the deal. The central limit theorem told us that if we take samples, those sample averages are going to be normally distributed. Okay? So we know that not only are those sample averages going to be normally distributed, but right in the middle of the curve, my population average is going to be there. So here's what we're going to do. So we have our population average right in the middle of this curve. Now what that means, let's say for instance that we wanted to find the middle 95% of this curve. So the middle 95% is going to have some sort of a value here and some sort of a value here, so that this middle 95% gets there. Now, what are these values going to be? Well, if you think about it, these values have to be a certain standard deviation away from our average. So what these values would be is our average, I apologize for that, is going to be our average plus some sort of, well, on this side, what's our standard deviation? It's sigma over the square root of n, but we'd have to go a certain amount of standard deviation jumps. So we'd have to go out some sort of a z value multiplied times our standard deviation divided by the square root of n. And what we're saying there, by the way, because this is symmetric, this left-hand side would also have to be that same average, but going back a certain number of standard deviations. Again, sigma over the square root of n. Again, sigma over the square root of n, I'm using that for my standard deviation because that's the standard deviation of the central limit theorem. So that's what's happening. Now, if you think about it, middle 95%, we can find how many standard deviations we have to jump back. We can find this z value. And we'll do that in just a moment. But what the central limit theorem says, now that we see it, is that there is a 95% chance that if I have a sample average, it's going to fall between this value and this value. So if I have a 95% chance that my sample average falls between this value and this value, I can use some algebra and solve that. So here's what I wrote down. Basically, what we're saying is because of the central limit theorem, we have a 95% chance that the average, my sample average falls between those two values I got. Now, the z value is the z value of alpha over 2. Again, I'm going to talk about how to calculate that z value in a second. And there we go. And so my sample average is a 95% chance I get between here and here. Now this looks an awful lot like this original formula that I gave you, except notice that the population average and the sample average have changed spots. So that's what I mean by using simple algebra techniques. You can subtract the sample average from all three sides of this inequality. You can subtract the population average from all three sides of the inequality, and then multiply everything by -1, and it turns out you come back to that. So you have a 95% chance that if you find a sample, that your population average is between your sample average minus that number and your sample average plus that number. Okay, so that's how the z interval comes out of the central limit theorem. Now let's talk a moment about these z values and what they are. We saw pictorially that these z values are corresponding to a certain number of standard deviation jumps. And think about this is middle 95%. That's how confident we were. That was our confidence level. So we had a 95% confidence level. How would I find a z value if the middle number were 95%? Well, what I would do is I would take and I would say, well, in order to find this z value, what we would need to do is find the area from negative infinity up to this value. And if we're talking about z values, that's just on the standard normal curve. So all I would do is just like we did in chapter number excuse me, the chapter 6, where we did the inverse normal function, all we have to realize is that, well, this is 2.5% of the data from negative infinity up to this value. So in order to find the z value, we go inverse normal, 0.025, comma 0, comma 1. And what we get is that this z value here, z value, would have to be a negative 1.96. So that's what I get for this z value. And again, that came out from 95% in the middle. That means 5% is on the outside. It has to split into two sides. So this left z value would be negative 1.96. Now, interestingly enough, because of the symmetry, this right, the z value would be a positive 1.96. So we can talk about this z of alpha over 2. And that's how this works. So here's the deal. 95% confidence level. We had a 5% chance that something fell on the outside. In other words, 5% chance was both sides. The way you should think about that 5% is you should think about it in terms of getting it wrong. We're 95% sure that we get it right, so we have a 5% chance that we get it wrong. Now, I'm going to create, instead of writing alpha as 5%, I'm going to write it as a decimal, 0.05. So I think of alpha as the chance that I get it wrong. So if you have a 95% chance you get it right, the chance you get it wrong is 0.05. The z of alpha over 2, well, the reason we just basically divide alpha by 2. So in this case, it's 0.025. So we take that 0.05, divide it by 2, and you get 0.025. So alpha is the chance of being wrong. Alpha over 2, we divide alpha by 2. And then in order to get the z value that I want, well, I'm just going to put in inverse norm 0.025, and this is why we use alpha over 2 with the z value. So we go inverse norm 0.025, comma 0, comma 1. Now, if you do that, you get a negative 1.96. Okay? What we're going to do is we're going to treat that as a positive, well, we want it to be a positive number. Let me try to get this way. Dang it. So what I'm going to do is I'm going to go inverse norm 0.025, comma 0, comma 1. And then I'm going to take the absolute value of it, which just means that I'm going to lose the negative sign there. Hopefully that makes sense. If it doesn't make sense, let me know. But essentially, the point of this is that we're using the inverse norm of alpha over 2, okay, to get that number. So inverse norm of alpha over 2. And again, we're doing the positive 1.96. The reason I use positive 1.96 is because, well, the left hand already has a minus sign on it. The right hand side has a plus sign on it. So the positive 1.96 would be this one. The negative 1.96 would be this one, since we already have a negative sign, so that we don't have like a negative of a negative. We'll just use the positive z value every time. So when you fill out a chart like this, what you would do is you would just take and write positive 1.96. Okay, hopefully that makes sense. Let me do one more just so that we can get this understanding. So if I'm 99% chance that I am right, I have a 0.01 chance of being wrong. That means each of the two tails will be of size 0.005. When I take inverse normal of 0.005, comma 0, comma 1, you get a negative 2.58. And so my z value is going to be a positive 2.58. Okay. So in short, this is inverse, I should say absolute value. I keep forgetting about the absolute value sign. Absolute value of inverse norm of alpha over 2. Again, comma 0, comma 1. Dang it. Let me act the way I was supposed to do. Alpha over 2, comma 0, comma 1. What is going on there? All right, let me try to redo this just a bit. There you go. So inverse norm of alpha over 2. That's how I get my z value. Again, hopefully that makes sense to you. What I'd like you to do is fill out the rest of this z values table. All right, if you didn't push pause and try that, then you should have. Do it now. Otherwise, I'm going to fill this in. So for the 92% chance I get it right, I have an 8% chance I get it wrong. That means each tail is size 0.04, and then I take inverse norm of 0.04, and I got a z value of 1.75. 90% chance we get it right means I have a 10% chance I get it wrong. That means each tail is size 0.05. When we do that, again, I'm rounding all these to 2 decimal places because that's what we do, right, on everything except for probabilities. So 1.64. 84% would mean a 16% chance we get it wrong. Each tail would be size 0.08. And when you do your inverse norm of 0.08, that turns out to 1.41. Again, we're using the positive 1.41 in our z of alpha over 2. 80% chance, well, now you get the picture. 20% chance we get it right, 10% chance in each tail. Inverse norm 0.10, and you get a 1.28. Why do that? Okay, and a 50% chance, again, these last couple would never come up in a real confidence interval scenario, but it is nice getting the practice of trying to fill things out and getting the point of it. So 50% chance I get it right, 50% chance I get it wrong. That means each tail is size 25% or 0.25. When we type that into my inverse norm, I get 0.67 as the z-value. So here's a couple things hopefully we notice. Obviously, if you want to be more confident, we need to go out further in terms of how many standard deviations we go out. And that should make sense, that to be more confident means I'm going to cover more of the normal curve. In order to cover more of the normal curve, I need to go out further. I need to go more standard deviations. So that's the connection between the central limit theorem. Now, what I would like to say now is, as far as these z-values go, like I said, there's two types of questions that we're going to deal with. The first type of question, when we find the actual confidence intervals, those z-values will sort of blend into the background, and we won't do a lot of calculations with them. But the second type of question, the one where we find sample sizes, we will definitely need to find and understand how to use these z-values. So on the test, you'll be given like a table like this, where it says confidence interval alpha, alpha over 2, z of alpha over 2. And you'll be asked to fill it out. And then when you need those z-values, you can go back and reference this table. And we will come back in this chapter and reference this table as well. All right, so let's start doing the actual calculations of the confidence intervals. So example 1 says a study of 35 golfers showed that their average score on a particular course was 92. The population standard deviation we know to be 5. Part A says what's the point estimate in this scenario? And then part B says find and interpret the 95% confidence level of the average score for all golfers. So here's what we do. First off, part A, point estimate. Point estimate is just that single number, right? So in this scenario, if you had a single number to guess what the population average is, you better say, well, the population average is probably close to 92 because that was my sample average. So point estimate in this scenario is 92. It's the guess that my average is equal to 92. Now, is that a perfect guess? Of course not. And that's why we do a confidence interval. We don't know if 90 would be close to that or if 83 would be close to that. So here we go and find our confidence interval. Now this is where the calculator once again comes in very handy. We could go way back up to our formula and say, well, our sample average is 92, confidence level is 95, so we could get a z of alpha over 2. The standard deviation, it tells me, the sample size, it tells me. So I could plug on all of that into the formula if I wanted to. But it turns out my calculator does that in a slightly more efficient way. And here's how the calculator does that. So let me write this down first, and then I'll show you what strokes I'm hitting. If you go into the stat menu and scroll over to tests, so stat, tests, and you scroll down, you will see number 7 and number 8 are z interval and t interval. So we go to number 7, which is the z interval. Now the reason we're using a z interval is because I know the population standard deviation. If I only had the sample standard deviation, I use the t. Now The display that you're going to see has an input, which right now we're given statistics. We're given a sample average, a population standard deviation, so on and so forth. So we're given statistics. So my input should be statistics. And then you see the numbers we need to plug in. Population standard deviation, well, we know that to be 5. Actually, I'm not going to write that down, all the plugins, but population standard deviation is 5. Your sample standard deviation, sample average is 92. Your sample size is 35, and then it should say sea level, and you can just put 95. Turns out you can put 95 or 0.95. The calculator will recognize either the percentage or the decimal value. And what I got is 90.344, comma, 93.656. Now here's what that is. So that is the confidence interval. So what we're saying here is, again, scroll back up to the formula or look up the formula. This formula says that the population average is 95% chance that the population average is between here and here. So in this scenario, we are 95% confident that the mean score, well, what would the population be? It'd be for all golfers on this course. Is between 90.344 and 93.656. Now, a couple of things to put into perspective. What does that mean? That means the average for everyone should be between there. Notice that this is the average for everyone. It's not saying everybody scores between those two, but rather that the average will be located somewhere between there. So it's very possible that an individual can get like 97 points or 100 points or point strokes, whatever. But the average, when you average all the golfers out, the average should fall somewhere between here and here. So there you go. So what we did is we just found the confidence interval, and then we just interpreted it as well. And with every single problem we do in this class, you're going to have to do both. You're going to have to not only find the confidence interval, but you're also going to have to interpret what that means. Like we did here, we're 95% confident that the average score for all golfers on this course is between 90.344 and 93.656. All right. By the way, that's exactly how we're going to interpret our results. Now, if you look at the book, the interpretation statements the book uses looks a little bit more like this. It says, we estimate with 95% confidence that the true population mean. And so, for instance, we would say we estimate with 95% confidence that the true population mean of all of scores for all people on this golf course is between blank and blank, 90.344 and 93.656. I don't like that. I think it's a little bit more clunky than the way I use. So the way I use is this option 2. And I say we are 95% confident that the mean score for all golfers on this course is between blank and blank. So I think that runs a little bit quicker and it's set a little bit smoother. So I use option 2 when I interpret results. If you wanted to read the book and use option 1, I don't like the phrase true population mean. I think that's a little bit redundant. So I just like to say the average for all, if that makes sense. So that's all we're saying. Now again, we need to make sure we understand what we're saying here. We are not saying that all individuals fall between those numbers. We're not saying that 95% of individuals fall between those numbers. Maybe only 1% of individuals fall between those numbers. But we are saying that the average of the group is between those two numbers. So hopefully that makes sense. The average of the group is between those two numbers, but that does not mean every individual is. In fact, most individuals might be outside of those two numbers. So here's what I'd like you to do. I'd like you to push pause and find and interpret the 95% confidence interval of the average IQ level for all voters in the United States. All right, so hopefully you went and did that. Now, I am going to use the calculator on this one, and I'll display the calculator this one time. So first off, let's go and see what we have. We are trying to find and interpret the 95% confidence level of the average IQ level for all voters. Now, whenever we type this in, what things are going to be needed? Well, we know that my sample average, let me write this down here, my sample average, we say, oops, is 98. My population standard deviation, it says is 15. Let me write that down again. It says my sample size is 50. And it says my confidence level is 95%. So you can either write 95 or 0.95 either way. Okay, so those are the things that I'll need to input in my calculator. And we'll need to input them where it asks me to input them. Now, before I move to the calculator, I want you to notice we have the population standard deviation given to us. It's 15. So because we know the population standard deviation, we'll use the z-interval. So here's where our calculator is at. If you had trouble finding it the last time, that's fine. We go to Stat, scroll over to the tests, all the way down at number 7. You can see there is the z-interval. So we're going to hit Enter. We're going to use stats as our input. My population standard deviation is 15. My sample average is 98. My sample size is 50. And my confidence level is 95. So we hit calculate on the z-interval, and my interval comes out to that. So I know I did that fast, but really it's pretty straightforward. If you are having trouble, let me know. We can do that. So I got 93.842, comma 102.16 for my interval. Now, how would we interpret that? We would say we are, or I am, doesn't matter, 95% confident that the average or the mean IQ level for all US voters is between 93.842 and 102.16. All right, so that would be finding the confidence level and interpreting. Okay, again, we're using the z-interval because we know the population standard deviation. All right, so there you go. So we're 95% confident the average IQ levels for all voters is between those two numbers. So let's understand if we can, let's try to understand what this is telling us and what it's not telling us. If somebody claimed that the average IQ level of voters is below 85, would that be believable? We should say no, it's not believable because our data suggests that the average IQ level is between 93.842 and 102.16. So if somebody said that the average IQ level of voters is below 85, that would not be believable. However, if somebody said they knew somebody who had an IQ level of below 85, that would be believable. Many people fall outside of the given range, right? Many people would fall below 93 and above 102. But the average of the group should be in the range given, in the confidence level, confidence interval that we've given here. All right. Hopefully that all makes sense. The wrong button. Now at this point, I'm going to stop this video, and then we're going to do a bunch of other examples on the next video, and we're also going to come up with how to use the t-interval and how to use the proportion interval. Remember I said there was 3 intervals that we had, a z, a t, and a proportion interval. So all 3 of those we will work with in the next video.